N, maximum of N. Where is that? Some elements in list of return values are undefined. List of return values are, okay. So now, whatever is that, A is equal to AI. Okay, so now let's check. So now, this is your orientation and the vector orientation for a given theta of 10, 10, 10, and then we are, okay, let's give it the exact value as this anthropomorphic arm. So we say, for example, let's just say theta is equal to 10, 10, and 10. Okay, that's theta. We say alpha is equal to pi divided by 2, 0, 0. Okay, I just omit the d is equal to, omit the comma. D is equal to d1 is 0.3. Let's say, for example, is 0.3. We copy this exactly. We copy that, and then 0, then 0 and 0. That's D. And then alpha is equal to 0, 0.3, and 0.3. We copy exactly this. No, that's alpha. This is A. Okay, so A is A, the 0, we say 0.3 and 0.3, we'll just say 0.3, and then D is also 0.3 and 0, 0. Okay, now let's go to robot kinematics, and then you have theta, alpha, and D and A. Okay, so we get the same thing. No, we don't get the same thing because we have different values. So now all we need to do is just change the theta value. Okay, for example, if you change the theta to be 30 degrees, maybe this is 90 degrees, and okay, let's make sure that these are converted into radians, because we say that this has to be radians. Okay, so input angles, we say here accept these parameters, and we say that the angles should be in distances in meters, and angles in degrees. Okay, so we accept angles in degrees, and so what we do here is theta times equals, does this one applies to, I'm not sure it applies to MATLAB. Okay, never mind. Theta is equal to theta times, do you have degrees to radians? Okay, so you have degrees to radians, and then that's theta. And you have alpha also converted to degrees to radians. Okay, so now there's some inconsistency that we have. Okay, we're going to, and then the distances, no need to transform. So in what we are giving is that for alpha, theta is in degrees, so your alpha should be in degrees, whereas, why? The kinematics, okay, let's just do this alpha. Okay, it has to be in terms of degrees, copy and paste, because we are already giving it, okay, this is 90 degrees positive. Okay, now theta was also in terms of degrees, yes, and so what we need to do is just call this one. Okay, so now those are 0.5. What about this distance? Is it around 0.9 because 0.3, 0.3, 0.3. Okay, let's see. For example, we want to have, where is your theta that is 0? Is theta 0 up? Okay, let's just say theta 0, 0. Okay, let's assign theta to be all 0, 0, 0, 0. Okay, and then kinematics. See if we have 0.6. All 0.6 will be the x is 0.6. So in x you have 0.6. So that means this robot is over here. This length is over here. Okay, this theta goes here, 0.6, and then the height of z is 0.3, so 0.3, and then yes. Okay, now and then what happens is that when that happens, where is your n effector? Your n effector, your z is in that direction, so your z is in the minus y, so minus y is your z, so minus 1, your z, okay, your y is in the minus z, and then your x is in the, where is that, this is the x, yeah, your x is in the y, your x, okay, wait, the y is up, z is in the minus y, so y is minus z, correct? No, your z is in the minus, oh no, your z, this is the z of the n effector, it should be minus y. Ah, does that make sense? Okay, your x, it says here your x is the same. I cannot, okay, just here. Okay, so if your, okay, can we do this? No, okay, let's just delete that. I want to check the forward kinematics if it's correct manually by looking at the annotation. Come on, where's the annotation? Okay, and then erase. Okay, so now let's annotate here. Let's annotate and then draw. So if this is your z0, okay, and this is your x0, and this is your y0, that's y0, okay. So if you do that, and this is your z0, let's just do that here, okay. And your theta is from x to what is your theta? The rotation about z0 from x0 to x1. Where is your x1? X1 is here. So that means 0 x1 should be here. Okay. When it's 0 x1 should be here. And so when that means this length here should be at the, it will be like that. Okay, and I'm just trying to draw the 0 of the the 0 configuration of the robot. So if that is the case, so your Z3 will be there, Z3, okay, and your X3 will be moved forward, X3, sorry, X3, okay, and then your y3, your y3, your y3 is in the z0 direction. Okay, so your y3, there's something wrong. See, in this case here, your x is the same as x, your x3 is the same as x0, so x3 is the same as x0 with respect to the base frame. So the x is here, so that is your x with respect to the n effector frame, with respect to the base is over here. So y with respect to the n effector frame. So your y is what? Your y is z positive. Now this is why I don't understand why this is there something wrong? Or maybe the zero, I'm not, I cannot see exactly if theta is zero. If theta is zero, so if theta is zero here, the z, your x and the x will be coincident, yeah? So your x0 and x1, this is x1, they're coincident, okay? And then your theta 2 is this, okay? So that means your x2, where is your x2? x2 is in this direction, x2 and x1. Ah, from x, from x2, okay, about z1 from x1 to x2. Where is your x1? x1 is there, and your x2 is also there. x1 and x2 are there, and then x2 and x3 are there. So yeah, that's correct. So I don't understand why. So if I were, so if I give out my opinion, the x will be 0.6 from here. This is correct, 0.6 and 0.6. And then z is 0.3. But the rotation from, in this case here, the z is a minus y. The z is a minus y. So that means, yeah, because this is the n effector. This is the n effector with respect to the base. So now the n effector is a minus y. With respect to the n effector, yeah, with respect to the n effector, the z of the n effector is a minus y with respect to the negative y. So is that correct? The z of the n effector with respect to the minus y, and then because this is with respect to the base. So that means that with respect to the base, where is your n effector with respect to the base? Okay, so where is your y-axis with respect to the base? If this is the y, I thought this is the n effector y, x, y, and z, okay, and then x, y, and z, and then how your y is seen from the x, y, and z of the base. So your y is seen, your y is a z axis from the base. No. It looks like, okay, we have to verify. I have to verify. If we say, for example, I thought this is x, y, and z from the n effector and x, y, and z from the base. It looks like this is the base and this is the n effector, the resulting x, y, and z, okay, from the n effector. So if that is the case, z of the n effector is a minus y. Okay, the z of the n effector is correct. The z of the n effector is a minus y, and then the y of the n effector is a z. The y of the n effector is a z, and the x, yes, it's correct. Yeah. So now we have already determined that it is somehow calculation-wise is correct in terms of the forward kinematics. Now let's go to the, how long have I been here? Okay, how long have I recorded? Did it show here? No, it doesn't show. Okay, anyway, so the same thing, this is just a forward kinematics. If we compute the Jacobian, now let's, okay, I'll create another video for the Jacobian tonight. Okay, thank you very much. Now I have to. Hello. So this is a continuation of our discussion on MCTE 512 robot motion planning. So there is a bit of correction, not just a bit, but a big correction regarding the rotation, the basic rotation matrices that we discussed a while back in the earlier discussion. I had a mistake in putting the sign of the off-diagonal terms for the rotation matrix. It was the other way around. What I wrote was the transpose of the basic rotation matrix. So from our slides, we say that for rotation about x, basic rotation about x by a value of alpha, so the rotation matrix will be like this. Previously, I put the sign negative here, but it should be a negative sign up here. Okay, cosine, cosine, and the negative sign here, and sine alpha. And for the rotation, basic rotation about the y-axis, I put the sign, the negative here. It should be the negative sign here, negative sign, and sine that's positive, and cosine, cosine, that's 0, 1, 0. That's the y. And about the z-axis is cosine and negative sign on top, and then positive here at the bottom, and cosine 0, 0, 1, like that. So that was the mistake that I did. That's why the result of it was surprising regarding the position of the n effector when we try to visualize and we try to verify through visualization of where could be the position of the n effector at certain configuration, easy configurations of, for example, where theta is all 0. Okay, so now let's try to do it one more time. So there was a mistake again in this case here. The alpha should be in terms of in terms of degrees, and that's is positive 90, and theta all 0, and then we run forward kinematics. What's the line 91 degree to radian? Line 91. What is wrong? Radian degree to degree, correct usage is degree to radian degree. Invalid call. Error code from print usage is line 91, line 45, and line 8, column 9. Line 8, here, it should be data. Mistakes. Okay, let's try it again. Okay, now this is correct now. So previously it was a transpose of this. So now if we verify that this robot is in so our x is 0 was here, and your y 0 was here, and if the configuration is 0, so that means that this has rotated, that is rotated already. So here we have to put the joint here if the rotation is 0, and the n effector will be there. So now it will have this as your x3, and then on the other side will be this is your z3. Sorry, Undo. Can I undo? No. I have to erase. Okay. So your z-axis will be here. That is your z3, and then your y-axis will be on top. This is your y3. Okay. So if you do that, so that means that your x3 is the same, the direction of x3 is the same as x0. Okay, so this is correct. This is the same as x0. Okay, I'll do a spotlight. This is correct. Okay, same direction. And your y3, the y of the n vector is the same direction as the z of the base. So y of the n vector, okay, here, this is the y of the n vector. So in the same direction as the z-axis. So this is the y, and now it is in the z direction. That's correct. Okay. So it becomes z direction becomes 0, 1, 0. So that means that from the z, when you look at your y component, the component of along the z direction is the y value of the n effector. That's correct. Okay. Now, when you have the this is the z of the n effector. So the z of the n effector is this in that direction. So the z of the n effector is the negative of the y. So this is the z, and you see that the z is the negative of the y. You can see that the y component here is negative. Okay, the negative of the y, exactly. So no component in the z x direction, no component in the z direction, but the component is the -1. So that means that your z is along the negative y direction. So z in the negative y direction. Now we are correct. Okay, I will upload this new corrected version because we have a basic mistake in the formulation of the of our rotation matrices. Thank you. Now let's end. Okay, let's continue. So we are done with forward kinematics for MCTE 521 robot motion planning. And we were able to create a function that computes the position and orientation of the n effector given the DH parameters theta, alpha, DNA. So now we are going to find the Jacobian and control the robot. So what we need to do now is based on the forward kinematics, we're going to compute given the DH parameters and DH convention, and we are able to compute the forward kinematics. Now we are going to compute the Jacobian to compute for inverse kinematics. As we know, the Jacobian is the linearized relationship of the rate of change of the joint angles against the rate of change of the n effector velocities, rate of change of the n effector position and orientation, okay, against the rate of change of the joint values. So analytically, this is how you compute your Jacobian. Okay, the partial of each of x1, which is, for example, the movement along x, with respect to each of the joint values up to n joint values, and then the partial of the y-axis movement, for example, with respect to each joint movement, and so on. And so the size of the Jacobian is m by n. Okay, now it is easier to consider the geometric Jacobian. Okay, so which is, in this case, we can consider a prismatic or a revolute joint. So let's concentrate on the revolute joint. Prismatic is where the joints are moving in a linear movement, and a revolute joint is when the joints are driven by motors, for example, and then it rotates, the joint rotates. So we will consider the joint movement of the joints that are rotating because it's a more complicated case. Okay, so now, for example, if you have an n number of joints, and so the column of your Jacobian will be according to the number of joints of the robot. So it will be because we're considering the velocities, so the velocity of the revolute joint will be based on the cross product of what is the joint velocity at joint n minus 1, okay? And then the rest of the links from n minus 1 up to n will be rotating based on the position vector. That is the translational rotation, or that is the translational velocity of the n effector. And for the pure rotation, the rotational velocity, it will be just the rotation about the z minus 1 axis. So that's the interpretation of the Jacobian column. So each of these columns will be based on zi minus 1, 0 from zi minus 1, for example, is about 0 to z0, cross with 0r 0, okay, and 0 pn. So that's the first column. For second column will be 0 z 1 cross with 0 r1, 1 pn, okay, and so on. For joint 3, it will be 0 z2 cross with 0 r2 and 2 pn, and so on. So let's continue. So now let's say we consider the anthropomorphic arm, and we have 3 joints, so that will be 3 columns. So in this case, we will be computing. We'll be looking at the Jacobian for specifically for this anthropomorphic arm. But when we write our equations, or we write our functions here, we will be considering a more general term. And so let's say, for example, you have function of j, which is the Jacobian. Again, you are given theta, alpha, and d and a, okay, and function. Okay, now so you'll be given all the alpha, you'll be given all this information of kinematics, DH parameters. So after given the DH parameters, you'll be able to come out with just the entire Jacobian matrix, okay? So again, we need to know what is the size of the theta, of the number of joints. And so normally in this case, we will compute the Jacobian as a full space Jacobian. And so we'll have 6 by the number of columns. So theta, again, we take the maximum, that is the number of columns. Okay, and your j will be equal to zeros of 6 rows, because it's a full space, 6 by number of joints n. Okay, so that's the size of our Jacobian. So now let's see what is J1. Okay, so J1, the first column, is this how you, okay, first column will be all this is all, what is this? All rows, first column, okay, will be equal to the cross of 0, Z0. Okay, where are we going to get this? We're going to get them from the transformation matrix. So now we are going to have 0, A0. 0, A0 is that, is this the identity, okay? Anything about 0, A0 is identity. Okay, there's nothing there. And so that's why your 0, Z0 is that your 0, okay, 0, Z0 will be equal to, this is 0, 0, and 1. Okay, and your 0p6 is the point. I'm just want to crudely compute first. So you have 0p6 or 0pn. Okay, this is the n. Okay, is equal to the you take the transformation matrix. Okay, I don't know if this one can do transform a from 0. and then we take only the, how do you take the, after you compute, how do you take the fourth column? Do we say, uh, okay, can you do this? All rows, or from 1 to 3 and then 4 column? I don't know. Okay, let's check first. Okay, this one. Okay, let's check if I can do this. Oh, let's check here. Can I do this one to extract the, I don't know. Check. Oh, it can. Okay, so that means that, so 0, okay, yeah, it's correct. So I can extract like this. Okay, so that's okay. Okay, so I extract here, so that's 0 pn. Okay, after from 0, because this is starting from 0 to end, from the base to the end effector. Okay, and the next we can 0 z1. Okay, 0 z1, for example, is equal to, okay, the transformation from theta 1. Okay, from theta 1, right? Okay, using theta 1 and alpha 1 and d1 and a1. Okay, and a1, and then now, what is this now? You transform and then you extract. You extract, this is 1 to 3. Okay, the first, I mean all the rows on column 3. Okay, that's 0 z1. Okay, and then 0 r1 is the same thing. Okay, this 0 r1 is equal to this one, but we extract the first 1 2 3 and then 1 1 2 3. That's the rotation matrix. And then 1p6. 1p6 is when you have what is that? Okay, starting from, because theta 1 rotates about base 1. Okay, so that means 0 to 1, so that means we go by theta 2 to n. Okay, how do we do the transformation there? Okay, so you cross with that one, and you, the previous m, I have to go, okay. Okay. Anyway, let's just let me not do the more general one, because it will take some time for me to think of how it will we efficiently compute it. Let's just do the 3 by 3 matrix. I mean the 3 degrees of freedom, and then the 3 degrees of freedom for the Jacobian. You can do it later on your own to have a much better computation, much more efficient computation in terms of indices for how do you put the indexing here so that you can compute, iteratively compute in a more efficient manner. So for me, I'll just try to compute manually. So we are going to have, in this case, okay, a new is equal to a, okay, maybe theta new, maybe theta t is equal to theta from 1 to, from 2 to 3, from 2 to n. Okay, not from 1 but 2 to n, and then because it goes through the next, yeah, this is theta 1, but then now you're going to consider starting from 2 to n. So now, because you're going to have 1 pn, so you have sorry, theta alpha d and a. So this is alpha, and then d, a, k. Okay. And then now you're going to do the transformation to collect 1p6. Okay, so 1pn is equal to the transformation matrix, transform a, this is similar to this one, I'm just repeating, but here you have theta t, alpha t, and dt and at. So 1, 2, 3, yes. So now you have your, so are you complete now? Okay. Okay. So maybe I'm just thinking whether I can, what is the best way to do this in terms of iteration. But anyway, so now we can say the J of all the columns, all the rows and the first column is equal to this one. Z, just follow the equation there, this equation, cross. Okay, when we say cross, how do we say cross? There are two elements in the cross. Okay, so we cross this one, cross like that, and this one, 0 pn. Okay, maybe we can. Okay, now 2 and 3. So 2, column 2 and column 3. Column 2 will be cross of 0, Z1, cross with 0, 0 R1 times, this is your 1 pn. So 1 pn, which is that one, based on the rotation of joint 2. Okay, rotation of joint 1, and then when you rotate about joint 2, it is based on frame 1. Okay. Okay. So now next is Z2, 0 Z2, and then 0 R2. It will be 0 R2, 0 R2, okay, times this is 2 PN. Okay, so that means that I still have to do this, okay, because this one is for, okay, so now you have you're going to have Z2 and 2, 0 R2 and 2 PN. Okay, so in terms of 2, 0 R2, it will be, now you have to make your theta. You have to make your theta like this. It will be from 1 to 2. Correct? From 1 to 2, 1 to 2, 1 to 2, from 1 to 2, from 1 to 2, from 1 to 2. And then here will be your theta t. Theta t looks like there's a pattern now, you can see. Later we can just change the AT. Okay. And then this is theta t, alpha t, dt MAT, and then that's the transformation. Now you need to have another, this one, another theta that starts from 2 to n. Okay, just follow this one. Okay, from not 2 but theta 3. Okay, theta 3 rotates about frame 2. Theta 3. Okay, now this is 2 and 3 to n. Okay, so now, so we have Jacobian that is 6 by 3. Okay, now let's just say J is equal to Jacobian. It's just a theta like that. Okay, so now let's see more general theta t, undefined theta t. Where is that? Line 34. Theta t, theta t. Ah, oh, okay. Okay, I don't have underscore. The same thing here. No underscore. Same thing here. No underscore. Okay, no more. And then that's that one. Okay. Oh, line 61. Cross at line 61. Go. Cross product of row by column. Okay, where? Okay, I'm not sure. Okay, maybe what line is this? Cross product of row by column, line 61. Line 61. There's nothing here. So maybe let's cross this one. Okay, maybe that's that one. I don't know. Okay. Still line 54, the same as last time. Yeah. Okay, maybe like that. The Z is this is a 3 cross product only applies to 3 by 3 by 1 by 3. Okay, that's 1 by 3. Okay, let's just do like that. See why? What's wrong with okay, let's see what are these values. Okay, okay, okay. That's 0, 0, 1, and that's okay. So non-conformant. So I thought you transform and then it's finished. It's okay. This is the transpose of that. And then what's the problem here? Non-conformant argument 6 by 1 equal line 54, column 10. Line 12, column 5. Line 12 is this one. Okay, Jacobian theta alpha d. Okay, and then you have cross of 2. Okay, whether we transform it or that one, I already did it. Column by column. Huh. Line 54, column 10. Why? This is already. You want us to do this? I'm not sure. Okay, now it's the same. So now they should be cross. Okay, now they should be able to cross because they are all column vectors. Jacobian line non-conformant argument is 6 by 1. is 3 by 1. What is 6 by? Ah! When we assign here. Okay. So this is just now because we are not considering. Okay. Sorry. This is just the position. This is just a position, and this is the orientation. Okay. So that means that this is 1 by 3. Okay, and then the orientation will be. Can I just add them? Okay. Yes. Like that. Can I just include here, and then you have 0, 0, Z0. Okay, can I do that? Okay, let's see. Okay, that's the Jacobian now. Okay, so we are fine. This one we don't need. Okay, now these two, 0, Z1, and then now again you have 0, Z1, 0, Z1. Okay, we'll check. There's the first column, second column, the third column. We didn't, these are all zeros yet because we assigned them to be 0 here, assigned them to be 0, and so we are going to assign the real values here. So that is the one cross with 0. What is this one? 0, Z2. Okay, let's see. Okay, so now, okay, so that's your Jacobian. So if only I can, is there a way for me to transform? Okay, we're done already. So we're able to compute the Jacobian, and then we should be able to use the Jacobian to control the inverse kinematics problem. So now what I'm going to do is, I don't know if I can generalize this on top of my head. Because this is identity. So 0, Z0 is the, maybe I need to assign identity, because here I need to assign something like this. Yeah, I can see the pattern, but it may take some time. Okay, maybe I can make a okay, AI IN n minus 1 and I n minus I AI, okay, is equal to identity 4 by 4. Okay, and then maybe we say, okay, for I is equal to 1 to n. Okay, and then we choose, because we prepare first, in a more general sense, we prepare something like this. Okay, so if we prepare something like that, we're going to prepare it here. Okay, so it will be with respect to theta 1. One to I. Oh, how come this is, there's inconsistency here. That's why it's not nice when you have, it should be D2. 3. Okay, so it will be for I is equal to 1 to I, 1 to I, 1 to I. And then you have your 0 ZI, 0 I. Okay, let's see the convention here. Okay, you have 0 Z I, and yeah, that's the I, the same as I. 0 Z, no, I minus 1. This is Ni, N minus 1, I minus 1. So minus 1. This is Mi minus 1. Okay, so you transform that, and then based on that one, ui plus 1. So ui plus 1. So you have theta I plus 1, I plus 1. Okay, another theta t, and then you use the theta t to in this case, you have I minus 1 Pn. So I minus 1 Pn. So that's the I minus 1 Pn. And then you cross. Okay. Okay. We don't need this. We don't need this. Okay. So Ji will be equal to cross of this one, cross with P, and this one. Okay. Let me check. Okay, wait. Is this correct? So you have identity here, and so you transform because if you have from 0, you start with, I want to include this one. How do I want to include the identity part? I can just say for I, but I don't want to do that. I mean, if I is not equal to 1. Okay. Uh, so where was that? Okay. Okay, let me. I have a ready program here, but I wanted to just do off the fly. Yeah, if you look at this, I cannot do it off the fly. So you transform, these are the transformation matrix from the identity. This is the the identity, and then to the next point. So we have done this already, and this is from m minus 1 up to n. So when you do n minus 1, that is your, this is the p, and then you cross with up to n. So now, once you do up to n, you subtract it, you transform it from 0 to n minus 1 by another transformation matrix. Yeah. From I here, you transform it with the next one. And so it will be for the joint 2. You prepare for joint 2. And then you can have the, after, okay, yeah, you have to play around with the indices. I cannot do off the fly now, but the idea is that if you check here, we were able to do it manually. Let's just put it back where it was, because I thought I can do it off the fly. I mean, on the fly. Is it on the fly? Okay, so because the nice thing about you automatically do it is because you can minimize errors in terms of indices. Like for example, this one, it should be from 1 to 2, 3 to n. Okay, but anyway, for a 3 by 3 matrix, this is what you have. I mean, for a 6 by 3 matrix, where the number of joins is n. Okay, so yeah, and this one will be your guide, and then you can, in your own free time, you can, yes, in your own free time, you can compose the Jacobian in a more efficient manner, more efficient than what I have shown here in my example. Okay, thank you.